So the work I will present is a joint work with Petr Golovach from the University of Bergen and with Charis Papadopoulos from the University of Ioannina. So I will be talking about square roots. So I will start by defining what a square root is. So we probably are familiar with this definition of the square of a graph. If you're not, the square of a graph H is just a graph G in which I add the edges between all the vertices that are at distance 2 in the graph H. And we call then H the square root of G. So for instance, in this figure, we have exactly this situation. H is a square root of G because if I add the edges in H between vertices that are at distance 2, I get G. But this is not the only square root that G has. For instance, this graph is also a square root for the same graph G. So from this, we can already see that a graph might have many square roots. And actually, some graphs don't have any square root at all, like C4, for instance. So from this, we see that, well, it's a sensible question to think of this problem. Given a graph, can we determine whether it has a square root or not? And this problem was already shown to be NP-complete quite some time ago. And there are two main ways that have been used to cope with this, with the hardness of this problem. The first one is to restrict the input graph G to belong to a specific graph class. And the second one is to actually require the square root to belong to a specific graph class. And this is the setting that we will be looking at here. And this gives the corresponding problem that we usually call it like H square root. So I want not only to find the square root, but I want the square root to belong to this prescribed graph class calligraphic H. So this problem has been studied by many people and there are many different results about it. And in this work, we will look at it from the point of view of parameterized complexity. So as I saw that the other works were concerning other topics and the audience might be mixed, so I decided to tell you the two definitions that we will need about parameterized complexity. The first one is that of fixed parameter tractability. So we have a parameterized problem and usually a parameter that I'll call K here, and a problem admits an FPT algorithm if this algorithm runs in time a function of K times a polynomial. So in particular, it means that for every fixed K, the runtime is a polynomial of the same degree. And the other important definition that I will want to use here is that of a kernelization algorithm. So this is a polynomial time preprocessing algorithm that will shrink your instance and output an equivalent instance that has size bounded by a function of K. So usually in parameterized complexity, we are interested in getting FPT algorithms and getting kernels that this function H here is a polynomial. So, so this is all you need to know about parameterized complexity. But again, we're doing parameterized complexity, we need a parameter. And here in our square root problem, our parameter will be what we call a structural parameterization of the graph class H. So for instance, instead of looking for a square root that is chordal or that is bipartite, we will look for a square root that has a certain parameter at most K, for instance, vertex cover. So this approach was first considered by Koshfer and others, and they did it with feedback edge set of size at most K. So feedback edge set is a set of edges that you delete and you get a forest. So they got really the algorithm, the results that you usually want when you look at a parameterized problem. They got a compression that is a polynomial compression and an algorithm, FPT algorithm, that is single exponential in K. So then we started looking at what happens if we consider vertex deletions instead of edge deletions. And already the first result we got is that if we look for a square root of vertex cover at most K, this problem, under like standard complexity assumptions, this problem cannot be solved in less than double exponential time, and also it does not admit a sub-exponential kernel parameterized by K. So this already shows that this problem will be harder than the edge deletion version. So we looked then at a parameterization that slightly generalizes vertex cover, which is the distance to a graph of degree 1. So we can always think of vertex cover as the distance to an independent set, because when we delete the vertex cover, we have an independent set. And we will actually look at the distance to a graph of degree 1. So more specifically, we will require that when we delete K vertices of this graph, we have a disjoint union of P isolated vertices and Q edges. And we will solve this precise problem in a runtime that is, of course, double exponential, as the lower bound also applies in this case. Yeah, and if you consider P being 0, or if you consider P being 0, then you have the distance to a matching, and Q being 0, you have again vertex cover. And if you try all possible values of P and Q, then you get the distance to a degree 1 graph. So in the remainder of the talk, I will give a slight idea of how the algorithm works, but I see I'm a bit short in time now, but I'll try anyways. So we want to look at the structure of a Ies instance. So it should look like this, right? The square root. We have this modulator, and outside the modulator, we only have isolated vertices and edges that have some neighbors in the modulator, and the edges might be of 3 types. These types are about like their neighborhoods. So type 1 edges are the edges outside the modulator that only one endpoint has neighbors in the modulator. Type 2 edges just means that these neighborhoods here are disjoint. The neighborhood of E and F are disjoint. And type 3 edges means that the neighborhood of C and D, they intersect in the modulator. And then we can see that if we have 2 isolated vertices with the same neighborhood, then they're true twins in G. And also the same happens if we have type 3 edges. Here I put A1 and B1 and A2 and B2. So the A vertices and the B vertices, they will be true twins in G. So far this goes well for an FPT algorithm, because it seems I have a chance of having a bounded number of classes of true twins in my input graph in case I have a Ies instance. And this is good because I can compute true twin classes efficiently, and if I see a large number, I can already say no immediately. Well, but this will not go as we want, of course, and this does not happen for the other 2 types of edges. But in this case, we see that the endpoints of these edges, they satisfy certain, like, their neighborhoods have some properties, and these properties will define an equivalence relation in pairs of vertices of the graph. And these equivalence classes will help us to do some pre-processing in the graph. What do I mean by that? Is that I will compute this equivalence classes, and if I find an equivalence class that is too big, and by too big I mean bigger than this function of K here, I am able to reduce the graph and preserve like yes or no instances. So I will do that. And this step is crucial because now I actually achieve a bounded number of true-twin classes in my input graph. So the number of true-twin classes will be this very ugly thing here, but it's a function of k and it's single exponential in k. So far so good. And if we see in this case, we're actually doing something better here. We are exactly bounding the number of type 1 and type 2 edges that a potential solution might have. This is not the case, for instance, for the isolated vertices and the type 3. I might have many type 3 edges with the same neighborhood in the modulator, or many isolated vertices with the same neighborhood in the modulator. So this I cannot, I don't know yet. But for the type 1 and the type 2, I can even guess how many I have because this is a function of k. So I will cope with this problem of the isolated vertices and the type 3 edges by defining a structure that I will be able to enumerate. So the size of this structure will be a function of k. And this is what we call a solution skeleton. So what will I do? Well, I look at a solution, and if I have multiple isolated vertices that have the same neighborhood in S, I will delete all but one. And I will do the same for the type 3 edges. If they have the exact same neighborhoods in S, then I delete all but one representative for that neighborhood. So I get this. And the type 1 and type 2 edges remain untouched. So now I have something very good because this structure has size bounded by k, and the family of all possible such structures can be constructed in time that is double exponential in k, so it's within my runtime bound. And then I will now tweak my question a little bit. Instead of asking for some square root, I want a square root given a particular skeleton and a modulator. I want to find a square root that has exactly that skeleton in that modulator. So, and this final step we do in the following way. So now we can make use of the fact that we have a bounded number of true-twin classes in G. And then for each vertex of our solution skeleton, we will guess to which true-twin class this vertex belongs. So we build this map from the vertex set of the skeleton to the true-twin classes. So of course, here we have to do some checks. For instance, we want that if two vertices are adjacent in the skeleton, or if they are at distance 2 in the skeleton, then they have to be mapped to true-twin classes that are adjacent, right? Otherwise, yeah, this mapping will not help us to find a square root. But once this is done, we have still something else that needs to be done, which is we have these vertices that we deleted in the skeleton, and we need to put them back. And to check whether it's possible to do so with the mapping that we created, we will solve an integer linear program that will have one variable associated to every vertex of your skeleton. And this variable will represent how many copies of that vertex I will add to the skeleton to obtain the square root that I want. And then we prove that we can find a solution if and only if this linear program has an integer solution. And by a result of Lenstra and Cannon, this linear program can be solved in time that is FPT in the number of variables. And therefore, it's also within our runtime bound. So yeah, that was a very brief overview and not detailed overview of our algorithm. And we, of course, have some other candidates to be considered. For instance, we really would like to know what it happens for the parametrization for a distance to a linear forest, and of course feedback vertex sets of the lower bounds that we obtained, they are still valid. So we don't expect to get things that are better than double exponential in K, but it would be nice to see indeed a double exponential algorithm or a better lower bound showing that we cannot achieve not even that in these cases, which we don't think it's the case, but it's a possibility. And yeah, I guess that's all. Thank you very much. If you have any questions, I'm happy to answer.
Are there any questions? Please come to the mic. No one? Okay, I have some very, very basic curiosity question.
Yeah.
Because I mean, I never. I mean, I knew what a square graph was, not a square root graph. I mean, it's a natural problem, but what about if you want to find a square cubic graph? Because it's natural to generalize this way. Can you somehow talk about the parameterized complexity of this problem?
Yeah, to be honest, I don't think it has been considered simply by the fact that the square root problem already becomes quite messy very often. So I don't think people feel motivated to consider higher powers.
But I think there will be different challenges, or the same techniques can still apply.
I don't know. I really don't know.
Yeah,
but of course, like there are many results that are like structural results on powers of graphs, right? And this already answers you the square root problem in many cases. For instance, if you have like a graph class and you know that every power of graph in that graph class remains in the same graph class, then this already tells you some information about the square roots of graphs that are there.
Okay.
Right. So if you look, instead of looking to square roots, you look to powers, to structural results on powers of graphs, then I think you can find a lot about higher powers. But from the point of view of parameterized complexity, I never saw, at least.
Okay. Thank you. Thank you again.